All right, let's dive deep into the world of hadrons. You know, the particles that make up pretty much everything we can see. And we're looking at an essay by Yurigo Schneeppert called Hadronen, Baustein der Quantentechnologie, which translates to hadrons, building blocks of quantum technology. It might sound a bit complicated, but it's surprisingly relevant to all of us.
Yeah, it really is. You know, we often think of atoms as like the most fundamental building blocks, but it's actually the hadrons inside the atoms, the protons and neutrons that give atoms their properties and really determine how everything interacts in the universe.
It's true. Schneeppert starts by kind of breaking down the word hadron itself, and it's actually got a pretty cool origin story.
Oh, it does. It comes from the ancient Greek word hadros, meaning massive, dense, or even strong. And that makes a lot of sense when you think about it, because hadrons are governed by the strong force, which is one of the 4 fundamental forces in physics.
Yeah, and this strong force, it's not just some abstract idea, it's literally what holds the nucleus of an atom together.
Right. Exactly. Without the strong force, all those positively charged protons in the nucleus would repel each other, and the whole thing would just fly apart. So it's this incredible force that binds quarks together to make hadrons. And then it further binds the hadrons together to form atomic nuclei.
So quarks are those even tinier particles that make up the hadrons. I always found it kind of confusing how they fit into the whole picture.
Okay, well, think of it this way. If atoms are like houses, then hadrons are the bricks. And the quarks are like the grains of sand that make up the bricks. And the mortar that's holding everything together, that's the strong force. So it's like this cascade of forces within forces, really, all working together to make the matter we see.
Okay, that makes it a lot clearer. But how did scientists even figure out that quarks existed? You can't just see them under a microscope, right?
Right. That's where these incredible things called particle accelerators come in. They're giant machines that smash particles together at unbelievable speeds. And by studying what comes out of those collisions, physicists could actually infer the existence and the properties of quarks. This all started back in the 1960s.
Wow. So it's like subatomic detective work. And that's when they came up with the term hadron, to classify all these particles that are governed by the strong force.
Precisely. And there are actually 2 main types of hadrons. Baryons, which are made of 3 quarks, and mesons, which are made up of a quark and an antiquark pair.
Antiquarks. That sounds kind of like Star Trek.
It does, doesn't it? But antimatter is a real thing, and every particle has an antiparticle counterpart, which has the opposite charge. So an antiquark is basically the antimatter version of a quark. And when a quark and an antiquark get together, they form a meson.
Okay, so baryons are like protons and neutrons, and mesons are like those more exotic particles.
Well, not necessarily. Protons and neutrons are definitely the most well-known baryons. But there are others out there. And mesons aren't always exotic. Some of them, like pions, actually play a really crucial role in holding the nucleus together.
Okay. Schneeppert also mentioned something called color charge. I have to admit that one always kind of threw me off.
Yeah.
Is it actually like the colors that we see?
No. It's not a visual color. It's more like a property of quarks that allows them to interact through the strong force. And there are 3 color charges: red, green, and blue. And of course, their corresponding anticolors. But the key here is that all hadrons have to be color neutral.
So do they all just have to be some kind of grayish color inside then?
Again, it's not about visual color. It's more about a balance. So a baryon, it achieves color neutrality by having 1 quark of each color. And a meson will have a quark with 1 color and an antiquark with its corresponding anticolor.
So it's like a balancing act with the colors, even though they're not actual colors.
Exactly. It's kind of a strange rule of the strong force, and it helps explain why you never find quarks just wandering around on their own. They're always confined within hadrons.
Wow. It's amazing how much is going on at such a tiny scale. Another thing Schneeppert mentions is that a hadron's mass isn't just the sum of its quark masses.
You're picking up on the really interesting parts. The strong force itself actually contributes to the hadron's mass. So it's not just the matter itself, but the energy that's holding those quarks together. That adds to the overall mass of the particle.
So it's not just the matter, but also the energy of the force that determines mass. That's kind of mind-blowing.
It is. And that leads us to some even more mind-blowing stuff. Exotic hadrons. These particles are really challenging our traditional ideas about how quarks can be arranged.
Okay, now I'm really intrigued. Let's unpack these exotic hadrons when we come back for part 2 of our deep dive. Okay, so we're back and ready to delve into these exotic hadrons, the ones that really shake things up. Can you give us a recap of what makes them so exotic? What sets them apart from those regular baryons and mesons we talked about?
Sure. So for a long time, Physicists thought that all hadrons were either baryons with 3 quarks or mesons with a quark and an antiquark pair. It seems like a fundamental rule. But then we started finding these particles that just didn't fit in.
And those are the tetraquarks and pentaquarks, 4 and 5 quarks instead of the usual 3 or 2.
You got it. First, we discovered tetraquarks with their 4 quarks, and then came the pentaquarks with 5. It was a real surprise, like finding a brand new element on the periodic table.
Wow, so how did scientists actually find these exotic particles? Was it through more of that detective work with particle accelerators?
Exactly. The Large Hadron Collider, that massive machine that smashes protons together at almost the speed of light, has been crucial in finding these exotic particles. Physicists can look at the results of those collisions and see signs of particles that act differently than anything we've seen before.
So why are these exotic hadrons such a big deal? Why are physicists so interested in them?
Well, it's not just that they're unusual. They're forcing us to rethink our understanding of QCD. The theory works great for explaining ordinary hadrons, but exotic hadrons push the boundaries.
So are they like breaking the rules of QCD?
Not exactly breaking them. It's more like they're showing us that there's more to QCD than we initially thought. For example, the way quarks are arranged and bound together in exotic hadrons is different from what we see in regular hadrons.
So it's like discovering new ways to build things with Legos. And those new creations are changing how we understand the connections.
That's a great way to think about it. These exotic hadrons show us new configurations of quarks and gluons, new ways that the strong force can work. And physicists are having to create new models, or improve the ones we have, to explain what we're seeing.
It's amazing how the universe keeps surprising us and pushing us to learn more.
It really is. And Schneeppet even mentions these hypothetical particles called glue balls.
Glue balls? What are those? Are they like hadrons but without any quarks?
Precisely. Glue balls are thought to be made entirely of gluons. The particles that carry the strong force, it's like the glue itself clumping together to form a particle.
Wow. So have scientists found any proof of glue balls yet?
Not definitively. They're very hard to find, and there's debate about whether they truly exist. The problem is, glue balls are predicted to be very unstable, and it's hard to tell them apart from other types of hadrons.
They're like looking for a needle in a haystack.
Pretty much. But the search is still on, and if we do find them, it would be a huge discovery. It would mean that gluons, which normally carry the force, can also act like matter themselves and form bound states.
That's incredible. So we have exotic hadrons changing our understanding of how quarks can be arranged, and then we have glue balls, which might completely change our understanding of what matter even is. It seems like hadron research is pushing the boundaries of what we know about physics.
It really is. And what's even more interesting is that this research isn't just theoretical. It's starting to have real-world applications, especially in cutting-edge technology.
I mean, there are practical uses for all
They're
this,
exactly.
beyond just understanding how the universe works.
Exactly. Schneeppet talks about how hadrons are becoming more and more important in fields like quantum computing and quantum cryptography.
Wow, that's really exciting. But before we get into those applications, maybe we should take a quick break and then come back for the final part of our deep dive into the world of hadrons. All right, so we're back and ready to talk about these applications for hadrons. It's amazing to think that something so fundamental to the universe could also be used to create these futuristic technologies.
I know, right? Schneeppet really emphasizes that connection in his essay, between basic research and these potential technological revolutions.
Yeah, so let's start with quantum computing. It's been a hot topic for a while now, but I'm still not entirely clear on how it all works.
Yeah.
How are hadrons involved in building these super powerful computers?
Well, it comes down to using the unique properties of hadrons, like their interactions through the strong force, to make and control these quantum bits, or qubits.
Okay, hold on. Remind me, what are qubits again? And why are they so important for quantum computing?
Sure. Qubits are like the basic unit of information in a quantum computer, just like bits are in a regular computer. But the difference is, a bit can only be a 0 or a 1, but a qubit can be both at the same time. It's kind of a weird quantum mechanics thing, and it lets quantum computers do calculations in ways that normal computers can't.
So are scientists actually trying to use hadrons themselves as qubits? I mean, hadrons are particles, right? Not like computer parts.
Yeah, it's a pretty radical idea, but that's exactly what they're looking into. They want to use those complex quantum states of hadrons, the ones that are governed by QCD, to build qubits. It's still early days, but it could really change everything about quantum computing.
So what's the advantage of using hadrons as qubits compared to other methods?
Well, for one thing, hadrons, like protons, are really stable particles. And that stability is super important if you want to build reliable qubits, ones that can hold on to quantum information for a long time. Plus, their interactions via the strong force are really strong and controllable, so you can manipulate the qubits more efficiently and reliably. That's essential for those complex quantum calculations.
So it's like we're using one of the most fundamental forces in the universe, the strong force, to control information at the quantum level.
Yeah, exactly. And it goes beyond just creating those individual qubits. Scientists are also researching how to use hadrons to create entanglement, where two or more particles are linked together and share the same fate, even when they're far apart. It's pretty spooky, but essential for building bigger quantum computers that can solve those really complicated problems.
Yeah, entanglement is definitely one of those things that takes a bit to wrap your head around. Okay, so what about quantum cryptography? Schneepapp mentions that too. He says hadrons can make communication more secure. How does that work?
Quantum cryptography uses these principles of quantum mechanics to make basically unbreakable encryption keys. And quantum key distribution, or QKD, is one popular way to do this. It uses photons, light particles, to send these keys.
Gotcha. So how do hadrons fit into this? Are they replacing the photons?
Not exactly replacing, more like improving the security. So researchers are investigating ways to use hadrons, especially those with unique quantum properties, like entanglement, to create even stronger, tamper-proof quantum keys. The idea is to use the way hadrons decay, or how they interact with other particles, to generate really random, unpredictable keys.
So it's adding this extra layer of quantum randomness to the encryption, which makes it almost impossible to crack.
Exactly. Hadrons have all these quantum phenomena that we can use to make quantum communication systems way more secure.
This is all incredibly cool, but I imagine working with hadrons at this level must be super challenging. It's not like you can just grab them with tweezers, right?
You're right. It's not easy at all. To work with hadrons and use their quantum properties, you need some seriously sophisticated equipment, like particle accelerators and these really advanced detectors. Plus, the theory behind it all, QCD, is really complex. You need powerful computers just to simulate and predict how hadrons behave.
So it sounds like there are lots of challenges, both in the experiments and the theory. But the potential rewards are huge.
Absolutely. If we can truly harness the quantum power of hadrons, it could transform a ton of fields, like computing, communication, even medicine and materials science.
It's amazing to think that it all starts with these tiny, tiny particles that we can't even see. It's a good reminder that when we explore the universe at its most fundamental level, we can discover some truly groundbreaking things. Well, I think that about wraps up our deep dive into the world of hadrons. Any final thoughts for our listeners before we sign off?
I think what I find most fascinating is how research on hadrons, which started out as this purely scientific endeavor to understand the building blocks of matter, has now become relevant to technology that could shape our future. It shows how science and technology are connected and how the pursuit of knowledge can lead to these amazing, unexpected outcomes.
Beautifully said. And for any listeners who want to learn more, I definitely recommend checking out Jörg O. Schneepapp's essay, Hadronen, Baustein der Quantentechnologie. It's a great place to start if you want to understand these fascinating particles and how they're impacting our world. So until next time, keep exploring and keep asking those questions.